Hi, everyone. This is Rob Gray from ASU and the Perception Action Podcast again. And this is the fifth article in my review series looking at some of my favorite articles from 2020. In this one, the topic is going to be focusing on the organization of degrees of freedom in movement and talking about motor synergies. What we're essentially talking about here, of course, is Bernstein's classic degrees of freedom problem. So I like to illustrate this with talking about serving a volleyball. The classic problem of Bernstein is how do we choose between the multiple, almost infinite number of possible options we have for joint configurations when performing a task like serving a volleyball, right? I've shown there kind of the state spaces for your elbow and your shoulder angle. How do we decide which of those to use? Which combination of shoulder elbow angles, and wrist angles in serving the volleyball, right? So that's the basic degrees of freedom problem that Bernstein proposed, right? And one of the main ways, and one of the best ways and highest level of ways, there's some lower level ways like freezing degrees of freedom that we solve this problem. But one of the higher level ways that we think you solve this problem in more elite athletes is through the development of motor synergy. So a motor synergy is when we take those degrees of freedom, those different possible joint configurations, and we essentially couple them. We make them co-vary so they work together in a synergistic fashion. Okay. So a motor synergy, it's a temporary organization of joints, right? We don't move our elbow and shoulder and wrist in the same way for every task we perform. It's very specific to the task we're performing. So in this, what's going to happen is the movement of one joint is going to compensate for the other. So they're going to co-vary. That's one of the ways we can solve the degrees of freedom problem. So I illustrate this in a volleyball serve. So if we have a volleyball, we've launched up in the air to serve, it's falling back down towards the eyes. It's closing this gap, which is specified by the optical variable tau, theta dot. That gap is closing with our eye. Our hand is also closing the gap with beta, which I call angle beta, and that the rate at which our hand is closing the gap is determined by the combination of the rate of change of our shoulder angle, the elbow angle, and wrist angle. So a synergy is if we have those different joints work together. So on some serves, we're going to have a bigger shoulder angle and a smaller elbow angle. On other serves, vice versa, and we're going to have different combinations. So they're going to co-vary and work together so as to satisfy the performance constraint and keep the constraint satisfied of getting the hand closing the gap in the hand, the beta gap, at the same rate as the optical gap of the ball, right? And I talked about this a lot more in my presentation that you can find online about coordinating degrees of freedom. You can see in this playlist on skill acquisition presentations. So that's the basic framework we want for this study I want to talk about, which is a really interesting study by a group of researchers. Toure is the lead author, but a couple of the authors I know quite well, and I love their work. First of all, Reinoud Bootsma is one of my heroes in research on perceptual motor control. He's done amazing work in a lot of different areas. And Raoul Bongers has also done a lot of work, particularly more on the rehab side of things and things like that. So they're both very excellent researchers. This study I chose, I like for a couple of reasons. One of them is it addresses an interesting question of how these synergies are formed, how they're shaped by the constraints of the task. Also, I chose it because it kind of illustrates a concept, right? In the very first article I reviewed of this, when I was talking about motor learning in a real task, I kind of critiqued basic research where people are using reaching tasks and very simple tasks in the lab. This is a really good example for me of when, in saying that, I didn't mean to say that those aren't valuable, right? Those have limitations in extending them to real world complex skills, but they can be very valuable in understanding motor control if they're used in the right way. And I think this is an excellent example of where a very simple task combined with a more complex one can be very useful in understanding motor control, and it's used in a really nice way. So I like this paper for that reason. So what they did in this paper, they were interested in how task constraints shape the synergies, the development of these synergies. And they were informed by an idea proposed by Kay in the 80s that constraints are going to act at two levels. First of all, they're going to force us to create the synergy in the first place, right? A certain combination of joint angles are going to work together. So maybe our shoulder and elbow for a certain task. Maybe for another task, it's going to be our wrist and elbow. And then within that synergy itself, they're going to actually act to constrain the actual outcome. So I like to think of this. I don't know if this is the way they would conceptualize it, but I like to think of this in terms of Newell's two levels of motor control. The first one is coordination, developing the basic pattern of movement, the basic synergy. The second one is control, actually specifying the values of the synergy to control the action, right? So constraints can work at two levels, forming the basic pattern of coordination, and then actually in terms of the actual specifics of the control. And to study this, they did it in a very interesting way, right? This is classic Reinhard Bootsma experiment where they design a task that has a real world element, but allows for comparison, right? It allows for things to be compared directly. So what they did was compare the tasks of reaching and interception, right? So what they had to do is a person sitting there controlling a movement of their finger along a rail. So they could only move it laterally. One task was basically a reaching task. So they had to move their finger to a static target, right? So the target could be at three locations, right? The end points of these kind of triangles at the bottom here. So you had to move the target. You could see it. It was sitting there stationary. You'd move it there, or you'd move it to the middle one, or you move it to the far one. So that was the reaching task. The task they compared that to was an interception task, right? So you were doing the same movement, right? Except in this case, the target was moving towards you, right? So you had to get your finger there at the right time to intercept it. And so critically, there's a couple of key things about this design why it's a really elegant experimental design. One is it involves the same degrees of freedom, right? In both these tasks, you have to coordinate your shoulder angle, your elbow angle, and your wrist angle in some way. There's multiple choices, multiple degrees of freedom you could use to do this task. How do you coordinate them to get to your goal? Okay. The other kind of elegant thing is the end point is exactly the same, right? That you're trying to get your finger to this spot, right? This one spot in space where the target is, but it's just getting the targets either stationary or it's moving there. They also added an important twist that I'll talk about in a bit, that the targets in the interception task, these different lines with the different colors, what they mean is in the interception task, the target approached the same point from different angles, right? So sometimes it went straight on to the endpoint. Sometimes it came from the left. Sometimes it came from the right. Okay. And that's a really important manipulation that replicates a really classic study that Pepper and Bootsma did in the 90s, right? Which was an important study illustrating proprioceptive control. Okay, and I'll show that the results, they basically replicated that here. Okay, so that's the basic test. They're going to compare. So they have two very different tasks, same joints, but one is the interception of a moving target. One is reaching to a stationary target. And within the interception task, they have these three different conditions. For the analysis to kind of look at these K two-step process, what they did was they first did what's called uncontrolled manifold analysis. And I've talked about this on the podcast a few times. If you want to look it up, I've gone into detail on a few episodes. My recent paper, I talk a little bit about it. Basically, in uncontrolled manifold analysis, what you're doing is you're taking the variability in movement and you're separating it into movement that takes you away from your task goal, okay, and movement that doesn't take you away, okay? So imagine the classic example Latache uses, this is one of his figures, is imagine your task is to push down on something so that you put 10 newtons of force, right? So you're pushing down with two hands, right? If you do 5 newtons in each hand, you satisfy the task. If you do 7 in one and 3 in the other, that satisfies the task, right? Any variability, like if you're at 5 and 5, right, and you increase both by 2, that's bad variability, what's called orthogonal variability, because that's taking you away from your goal, right? If you add 5 and 5, now you have 12, now you have 14 newtons of force. That's too much, right? It's taking you away from your task goal. The other type of variability we call variability along the manifold, which sometimes we call good variability, because this is variability that is not taking you away from your task goal. So if I went from 5 and 5 to 6 and 4, or 5 and 5 to 7 and 3, right? That's variability that's keeping the performance stabilized. It's satisfying my task goal, but we call that good variability because it allows for adaptation, adjustment to the different conditions, right? So that's the first thing they looked at. And the important point is, if we have a lot of this variability along the manifold, good variability, it's really evidence that there's synergies, right? That's where you see synergies happening. Variability, when I use more elbow and less shoulder on one trial and less elbow and more shoulder on another trial, that's going to show up as this good variability, right? Because that keeps me at my goal. The other thing they did was that once they identified these clusters, these kind of synergies, they looked at where they were in task space, right? So did they fall within similar areas of task space or different areas, right? So that's what they were looked at. And it was this paper is a very heavy paper, right? Very methodologically and analytically heavy paper. The analysis is very detailed and very complex mathematical process I'm not going to go into. But that's I'm just kind of describing basically what they did. Okay. What did they find? First thing they found, so these are the reaching profiles. So these are the profiles of your your finger velocity. So this is reaching to the 3 different target distances to the static target, those 3 lines. So we have your velocity over time, okay? Here is your velocity when you're trying to intercept a moving object, okay? So a couple points here. One is you were seeing a different movement profiles for the 2 different tasks. In the reaching task, it's very symmetrical, right? The peak velocity occurs about halfway through the movement for all the distances, right? So you're controlling the reach by varying the velocity, right? In the interception task, you can see it's very asymmetrical. The peak velocity, the maximum height of these curves is occurring earlier, and there's a longer deceleration phase. Also, this study replicates, as I mentioned, a classic finding that Pepper and Bootsma found, that what you can see is you get different velocity profiles within the same endpoint location. So imagine the target's going to reach the middle location, you get different reaching profiles for the different approach angles, right? And the reason this is important is because it demonstrates that what is going on is prospective online control, not predictive control, right? So think about it. If my hand is sitting in the middle and a target is coming, 2 feet to my left, okay, 1 foot to my right, say 1 foot to my right. If I have a perfect predictive model, as soon as the target starts moving, I predict that it's going to arrive 2 feet to my left or 2 feet to my right, okay? So I reach my hand there and I know when it's going to arrive. If I have a perfect predictive model, if I'm predicting the location, then it should not matter what angle it's coming from. It should not matter if it's coming from the left, it's coming from the straight on, or if it's coming right? Because in their conditions, it's going to arrive exactly in the same spot at the same time, no matter what the approach angle is, right? So if I'm using predictive control, trying to predict the future location of the target, there should be no effective approach angle. But they're in their famous study in I think it was 92 paper, there was, and you can clearly see it here. You get 3 different lines for the 3 different approach angles. That is what you expect if you're using prospective online control, okay? Because the information is different for the different approach angles, right? So it supports their evidence. And it also supports the idea within this study that the different constraints of the reaching versus interception tasks are organizing the system differently. And so let's look at that in a bit more detail. The next thing that they did was to look at the uncontrolled manifold analysis, right? So what this is showing is the blue dots are the good variability. So variability that keeps the task constraint satisfied, right? So in this case, it's the combination of shoulder, elbow, and wrist angles that keep your hand going to the right target location. The red dots are for the variability, bad variability, the orthogonal variability, that are combinations of those joints angles that are going to make you not arrive at the right location. And this is for reaching the ISO, or the interception for the 3 different approach angles. And overall, you can see that the variability along the manifold, the good variability, is higher in all conditions than the bad variability. And it's about the same for all the tasks, which suggests that people are coordinating degrees of freedom in this task by developing motor synergies, right? Because variability along the manifold, good variability, in order to have that, you have synergies between the different joint angles. So that's the first thing. So this supports kind of K's first step. In solving the problem, the first thing you do is you develop synergies. The next thing they did was look between the different tasks, look at reaching, and looked at essentially where the clusters lied in the state space. And again, this was a very complicated analysis I don't want to get into mathematically. But basically, what you can see here, these numbers represent the location in state space. And if you just look at the first one, you can see that all the interception tasks, I, all have roughly the same number in the 30s, right? So there was a lot of overlap in the synergies, the cluster. So there wasn't a big difference in the actual type of synergy you used for the different approach angles. But there was a huge difference between the clusters you use for interception versus the ones used for reaching, which are in the 60s and 70s, right? So these numbers are very different. Okay, so the actual synergies you're using, the area and state space you occupy, is very different for these 2 different tasks. Okay, so what is this showing? So for both of these tasks, we're seeing joint condition configurations that primarily show good variability, like covariation. Degrees of freedom are being organized in terms of motor synergies. We're seeing a large overlap within the different conditions. Okay, so within the different types of interception, there's large overlap in the location of these synergies, but there's little overlap when you create a different task, reaching. So the authors conclude, I like this, taken together, these results imply that some of the task constraints, whether the target's moving, whether you have to stop at the target, operate at the level of synergies, right? They create different synergies in different locations in different state space. While other ones, okay, which is kind of a coordination level, while other ones are going to operate, other task constraints like the approach angle don't affect the actual nature of the synergy where it is in state space, only affect the actual kinematics, the actual control itself, okay? And I really love this quote. In some cases, different synergies emerge, while in other cases, a similar synergy is constrained differently, right? So it's so these task constraints can operate either at the coordination level or at the control level. And this is, as I said, very consistent with the 2-step process proposed by Kay. Okay, so I think that's a really interesting paper. I encourage you to have a look at it. As I said, it's a very deep, detailed analysis. So if you're into this, you might see how they actually calculated those things. But again, I think it's a good example of using basic laboratory, very simple tasks with these kind of nice manipulations to address interesting questions in motor control. Okay, that's it for me. Remember, you can find everything about me at perceptionaction.com and about the podcast and so on. And we'll see you later. Thank you.